Hi, my name is Autumn McSwain, and this is my lab for magnetic backing with Faraday. So, to start with, the purpose of this lab is to study magnetic induction through the observation of a bar magnet falling through an aluminum tube. The results will be shown that the experimental time is 1.254 seconds and the computational time is 0.361 seconds. So, some fundamental concepts. First of all is Faraday's law, which states that a voltage is induced in a conductor whenever there is relative motion between the conductor and an externally applied magnetic field. The second fundamental concept is Biot-Savart's law, which states that a magnetic field is generated by an electric current. And then the final two concepts is Newton's second law and third law. His second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, which is why the summation of F will equal m times a. And the third law states that every action is an equal and opposite reaction. This explains how forces always come in pairs, which is also why F will have an equal and negative F. So, for the procedure, I was asked to take an aluminum sheet and roll it into a tube and then drop a bar magnet through it. This procedure is shown on the left, and it also shows the currents that are created by the aluminum foil and the magnet as it drops. So the system is the aluminum tube and the magnet, and the surroundings are everything else. And some assumptions are that air resistance is negligible, the bar magnet acts as a magnetic dipole, and the only forces on the system are the magnetic and gravitational forces, because F grav will work down, whereas F mag will work up. And we are able to assume that the bar magnet was perfectly vertical, and the foil roll was also perfectly vertical. So for my experiment, I had to drop this magnet through this tube of aluminum 5 times, and each of my times are recorded with a stopwatch on the right of the chart, and my average time came out to be t equals 1.254 seconds, which is my experimental time. And for my computational model, I needed the tube's dimensions and the magnet's properties, so I got the tube's length is 0.3 meters, the tube's width is 0.006 meters, the inner radius is 0.026 meters, and the outer radius is 0.032 meters. The magnet properties is that the mass was 0.025 kg, and it had a magnet of 4.613 A times n to the second. With this, I was able to work on my computational model. And for the beginning of my computational model, I had to discover my initial conditions. So first, I had to put the physical constants, which the new one is resistivity, which will equal 2.65 times 10 to the negative 8th. And the properties of the magnet are there, and the geometry of the tube is there. The important part here is the big chunk of code in the bottom left, because I was able to calculate the magnetic field of the bar magnet using the formula MO divided by 4 pi times 1 over r cubed. And then all of that was times 3, parentheses m times r hat, in parentheses r hat minus m. All of that times the initial stuff. And then I also was able to calculate magnetic flux by doing 3/2 times MO, absolute value of M times Y times the absolute value of V, R squared, all divided by R squared plus Y squared to the 5/2. So next I need to be able to calculate the forces because I stated before there's a magnetic force and a gravitational force. So F net will equal F grav plus F magnetic, and F grav will equal the vector 0, comma, negative mass times gravity, comma 0, because gravity is just mass times G, which will just be the downward force of the object. And then using Newton's second law, I was able to come up with a velocity and position update formula where ball velocity will equal bar velocity plus F net divided by mass times delta, and then bar position will be bar position plus bar velocity times delta. Furthermore, I was able to calculate the magnetic forces from the tube of the magnet. This took a lot, and I basically just had to calculate F on ring will equal the absolute value of I times 2 pi r times the absolute value of Bm times the absolute value of Um dot Bm. And that brings me to the end of my computational model. And the results were that it takes about 0.36 seconds for it to fully go through the tube. And as you can see in the graph, is that my when F grav is greater than F mag, it drops, and the green is what represents this, and it shows it entering the tube and exiting the tube, but in the middle of the tube, F grav is equal to F mag, and this is shown through this video. Note that the blue light is above and the red one is down, and that was my computational model. So some questions about the simulation. As seen before, there were colors. And so what color corresponds to the clockwise motion and which one corresponds to the counterclockwise motion in the current? Red is the counterclockwise motion, which was on the bottom, and blue is the clockwise motion, which is on the top. And this is shown by utilizing Lenz's law. Now, what would happen if I were to flip the magnet? If the magnet was to be flipped, the current's direction would be flipped, but the magnet would follow as before, as highlighted in the last lab. So the currents would just be switched. How does a real world total time in tube compare to the computational model? The computational data is shorter, which makes it not include air resistance and human error. These things would be improved in a real world experiment, which would improve accuracy, which is why the experimental time is 1.2, whereas the computational model is 0.3. What is the shape of the velocity versus time plot tell about forces acting on the magnet? The plot shape shows how the gravitational force is greater than the magnetic force when entering and leaving the tube, but it is equal within, which was shown by how F grav was greater than F mag in the beginning and at the end, but it was equal to each other before. Now, some error from this and why the 1.2 and 0.3 difference for computational and real world is human error, because there was definitely a tilt in both the bar magnet and the foil roll. Likewise, there are probably issues with the timing of the drop and other measurement issues. The next thing is air resistance, which is the force that fights against the moving object as it moves through the air. And then finally, there was friction because the magnet did not perfectly hold vertical. It kind of like wobbled. So it hit the side of the tube as it went through, which created friction, which further slowed the magnet down as it fell. So, what if the resistivity of the conductors were reduced as close as possible to zero? How the dynamics of the falling magnet change? If the tube's resistance was close to zero, this would increase the induced current, which would then produce a stronger opposing magnetic field. This will cause the magnet to slow down even more, and this idea is shown and supported by Ohm's law. Now, what if holes or slots were got in the tube? How would this affect the ring current in the model? If there were slots in the tube, this would cause there to be less current rings within the tube, which would overall produce a weaker opposing magnetic field. This would cause the magnet to fall through faster, and gravity would just be stronger than F mag. And this is because there would be a issue with the dispersion of electrodes across the object, because this would cause the magnet to fall faster, as the holes in the tube would interrupt this dispersion of electrodes. And that is my lab 4. Thank you for listening.